Okay, so we have the circuit and they're asking for the total current first. So for total current, IT equals VT over Z. We have our VT. Our VT it is 210. But now we need our Z. And to get our Z, we need all the resistances in the circuit. So we need to get this now. We need to now calculate this. So we have our R. Now we need to get our inductive reactance. So our XL equals to 2 pi FL, like that. Then we substitute our frequency of 50 Hertz, our inductance value, which is 0.12. What answer do we get? I got 12. Okay. I mean, now you can use that 12 pi. And the answer is in ohms, right? Should be in ohms. Then for our XC, we have 1 over 2 pi FC. Then we substitute. Our C value is 100 micro. So it's 100 times 10 to the power minus 6. And our value is 1 over 2 times. Do we get 31,831 ohms? Then for the impedance of the circuit, I use the big one because I have because I have a resistor, an inductor, and a capacitor. I have all three components, so I use the big one. Um, so let me write it here for space. No, yeah. So Z equals R squared plus XL XC squared equals R squared is 12 squared plus, so the bigger one is the XL, so I'm going to say 37,699 minus 31,831 squared. So my Z is going to equal 13,358 ohms. Did we all get that for the impedance? Then we just substitute that Z, our impedance, into this formula for our current because we're still there. It gives us 15,721 amps. So our current is measured in amps. So they're asking for the phase angle for number 2. So we have this one. Wow. What if I do this? Okay, I'm gonna work like this, yeah. So for phase angle, the formula for phase angle is secant function cos R over Z equals, our R value is 12, our Z is 13,358. Gives us 26,06 degrees. Did we all get that one? Lovely stuff, lovely stuff. Okay, so now they're asking for the voltage drop across the resistor, the voltage drop across the inductor, the voltage drop across the capacitor. So for the voltage drop across the resistor, we need the current going through this resistor. So we need the I total, because in a series circuit, the current is constant throughout the whole circuit, right? So we need the current going through this resistor, and we also need the component's resistance. So we're going to say ID times R, which is our Ohm's law. So 15,721 times 12 is our VR. And we are left with 188,652 volts. Then for our inductance, the voltage drop across the inductor, the very same thing. We need the current going through this inductor and the inductor's resistance. So then the name of the resistance for the inductor, it is XL. XL. So we substitute 15,721. Our XL value was 37,699. Our VL equals 37,699 is equal to 592,666 volts. The voltage of the inductor will always be bigger than the other voltages. Okay, so we need our VC, the voltage across the capacitor. So the current to the capacitor and the capacitor's resistance we need. So I total times XC equals 15,721 multiplied with 31,831. Then they're asking for the resonant frequency. So this was actually number 3, number 4, number 5. Then for number 6, they want the resonant frequency of the circuit. And the formula for resonant frequency is just number 14 over here. So we write 1 over 2 pi square root LC. Then we substitute. So we got 0,12 times 100 times 10 to the power minus 6. So the resonant frequency equals to 1 over 2 pi 5,944, and frequency is always in hertz. Can everyone get the resonance frequency correct? Oh, it's just us now. The other guy left. Okay, not a problem. Did you get these answers, Manier?
The frequency,
Oh, okay. Okay. Yeah, that value is a bit too big, too much out there. Mm, yeah. Okay, cool. As long as you see. Okay, lovely. That's perfect. That's perfect. Okay. Let me see what else is here. Let me see if I have that calculation. Maybe there's an example. So, let me see. At resonance, impedance equals resistance, inductive reactance equals capacitive reactance. And then our current is at maximum. But these two are very important. Um, I don't think you'll be exposed to calculations of this, but I will go to some question papers if I have time, and then I will look if they have a question on this with RLC circuit, because it's a very simple calculation when they are at resonance. Um, but yeah, Z equals R and XL equals XC. It's very important for the calculations. Um, and why that is, right? There's a reason for that. Let me try and find the diagram. So where is the understanding? Yes, I see it. I see this. But so the curve I'm looking for, what I'm looking for, right, is basically it's okay. Let me try and draw it. So it's this, right? So you know that on this other one that I did yesterday, where is this thing? Okay, page now. That page now isn't here. But so this graph, right? We have our little our objective diagrams, and we have our XL there. We have our XC there, our VR, and our I. Uh, yeah, it's our R. It's our resistor. Okay, let's say it's that, right? What this is saying is at resonance, XL equals XC. So we know that these are gonna subtract from each other, but because because XL equals XC, like they are they have the same magnitude. They have the same magnitude in like, so they have the same size, right? So when they get subtracted from each other, like this here, yeah, when they get subtracted from each other, you're gonna get zero. This is why you can see, yeah. think that on that page 46 it explains it nicely. Yeah, yeah, you see the exact same thing. When you subtract them from each other, you get zero. That is why when you square root that r squared, you get z equals r. But it's also from the graph. These cancel. They cancel each other. And you're left with just the r for your resistance or your impedance. And yeah, so we know that, let's say there was a difference here, and then our xr minus xc ended there, and we will throw uh, that vector for our impedance. But because they equal zero, they ending here by xr minus xc, it's on zero. That means my z will also lay on this line. It will lay on this line. That is why z equals r. It's just some small theory, not very important to know, but I just wanted to understand like where this is coming from, and at resonance, uh, what it actually means. So at resonance, your z equals r because your xl is equal to your xc, and these, they have the same magnitude, but they go in opposite directions on your vector diagram. That is why it's actually a phasor diagram, but yeah, it's a vector diagram. But yeah, okay. I think that covers it all for RLC circuits. So if you can do this big one, you can definitely do the small ones that with it's either with the resistor and the inductor or the resistor and the capacitor. But okay, um, that covers it all for the RLC circuits. But I will look for more questions if I can. I have time. If I have the time. Okay. Um, I don't know what I did with that page for the scope, for the scopy. But do you want to? Let me find my phone. Do you want to perhaps go through things for the test? Because RLC is covered for now. If you can maybe rewatch the video of yesterday, that can be helpful for you RLC. But let me actually do this. Yeah, let us go to other work maybe, and then we see from there.